A multi-point tool has two or more chip-producing edges on a common body and is rotated to cut. Some examples of multi-point tools include face milling cutters, end mills, drills, reamers, and taps. Let's explore multi-point tools by focusing on face milling cutters. Face milling cutters effectively generate flat surfaces with the spindle perpendicular to the work surface. The cutter body has multiple pockets to accept a variety of indexable insert types. As the cutter rotates, each insert edge alternatively enters and leaves the cut, removing a small amount of material in a short, discontinuous chip. The chip thickness at the start of the cut is called the undeformed chip thickness. Most milling with indexable insert milling cutters is performed using the climb milling mode, with the insert biting into the thickest portion of the chip first and then thinning towards zero upon exit. This is the reverse of the conventional milling mode, in which the milling cutter bites into the minimum chip thickness at the start of the cut and exits at the maximum chip thickness. The milled surface results from the combined action of cutting edges located on the periphery and face of the cutter. The flat milled surface has no relation to the contour of the individual teeth, except when milling a shoulder. Not all face mills are used for large, straight cuts. Some small diameter face mills are used to ramp into a surface, then plunge to a depth, and interpolate outwards to mill a large pocket more efficiently than an end mill could. There are major variables in the design of face milling cutter bodies which must be considered when selecting tools. These include the cutter's diameter, the hand of cut, the cutter geometries, including rake and lead angles, the insert pocket design, the milling cutter pitch, and the cutter's mounting method. For cutting, the effective diameter is the most significant concern. The effective diameter is measured from the highest point on an insert on one side to the highest point on the insert on the opposite side. For proper positioning, the face milling cutter's effective diameter should be about 1.5 times the width of the cut desired. This allows 1/4 to 1/3 of the cutter to overhang the edges of the workpiece, providing optimal chip formation. If the diameter of the face milling cutter is the same as or barely larger than the width of the workpiece, then the chips generated will be too thin at the entry and exit of the cut. This results in a buildup of heat and friction, which will reduce tool life. The hand of the cutter is determined by examining the cutter's face while running on a machine tool. A right-hand cutter rotates counterclockwise, and a left-hand cutter rotates clockwise. Rake angles in milling cutters are determined by the cutter body and by the insert. Two rake angles, the radial rake and the axial rake, are determined by the position of the insert pockets in the cutter body. The radial rake is the angle measured between the insert face and a radial line drawn from the cutter axis to the cutting edge, hence the name radial rake. If the insert tilts toward the chip gullet, it has a positive radial rake. If the insert tilts away from the chip gullet, it has a negative radial rake. The axial rake is the angle measured between the insert face and an axial line or plane, and it may also be positive or negative. The combination of axial and radial rake angles yield 3 geometries of milling cutters: negative radial and axial, which offers the strongest edges but generate the greatest cutting forces; positive radial and axial, which provides the freest cutting; and negative radial, positive axial, which presents a strong edge to the work but pulls the chip up. The rake angle on the face milling cutter inserts, in conjunction with the cutter body's radial and axial rake angles, contributes to the cutter's effective rake. The cutter's lead angle influences cutting forces and chip thickness. The greater the lead angle, the greater the axial force, and the longer but thinner the chip. Standard milling cutters come in 0, 15, 30 and 45-degree lead angles. Most face mills are designed with insert pockets that are fixed. Other cutters are modular and accept a variety of interchangeable insert cartridges that hold various insert designs and seat the inserts at different angles. This allows the orientation of the inserts to be varied using the same cutter body. The pitch of a milling cutter is determined by the number of inserts in relation to the cutter diameter and can be defined as the distance from a point on one edge to the same point on the next edge. The coarser the pitch, the larger the chip gullet. Gullet size is important in face milling, since the chips are generally confined to the gullet until the insert exits the cut. Cutters may be coarse pitch, fine pitch, or extra fine pitch. Fine pitch cutters are used primarily for milling cast iron or for finishing work. Coarse pitch cutters provide a large gullet space necessary for milling ductile materials or in wide cuts. They are chosen for everyday work. Milling inserts are available with various grades and shapes. In addition, milling inserts have their own corner geometries, including the radius and the wiper flat. A large corner radius produces a finer finish than a small radius, but a corner wiper flat on the insert produces the finest surface finish. Sometimes a single wiper insert in a cutter will improve the surface finish, even if all the others are roughing inserts. For best surface finish and longest tool life, all inserts must be preset to carry an equal load. One or two inserts protruding further than the others will carry the cutting load and wear out prematurely. To hold close tolerances in milling, a very stable mounting is essential. There are several methods of mounting face milling cutters. Milling cutters under 3 inches in diameter are usually integral shank cutters. Face mills between 3 and 8 inches in diameter are mounted onto an adapter and go into the spindle. Face mills from 8 inches diameter and up may mount directly to the spindle. As an introduction, we've covered only a few of the many aspects of milling with carbide tools. Extensive calculations are also involved when choosing effective cutter types, cutter paths, and cutting parameters. Let's re-examine the material contained in this videotape. Cutting tools cut with an edge, and those edges can be described by their geometry. For metal cutting efficiency, it is critical to select the edge that cuts best, given the material and cutting conditions. The purpose of the edge and its geometry is to create a chip. The right geometry creates chips cleanly and efficiently. The wrong geometry may not cut at all, or cut poorly, fail prematurely, or damage the workpiece surface. Cutting tools fall into 2 broad classes: single point and multi-point tools. Turning uses single point cutting tools, usually coated indexable carbide inserts. Selecting turning inserts involves choices of insert grade, geometry, and tool holder design. The geometry of an insert includes its shape, relief or clearance angle, tolerance, type, its inscribed circle or IC size, thickness, nose radius, and the insert's chip breaker design. The largest influence on chip flow in turning is the top or back rake angle. This is the angle created by the top of the cutting tool and an imaginary line drawn horizontally through the workpiece diameter. A positive rake cuts freely. A negative rake is stronger but generates more force in cutting. The tool nose radius helps determine insert strength as well as workpiece surface finish. Insert size is designated by its inscribed circle, and the inscribed circle size of the insert must match the pocket size of the tool holder. In turning, making a chip is only half the battle. The other half is effectively breaking the chip with the right chip breakers and operating parameters. Tool holders and boring bars may be designated by their shank size, hand of the tool, method of clamping, insert shape, insert size, insert style, and rake angle. Multi-point tools rotate to cut. Face milling cutters are a type of multi-point tool. Face milling cutters vary in diameter, hand of cut, geometry, pitch, insert pocket design, and mounting method. The two rake angles determined by face milling cutter bodies are the radial rake and the axial rake. These two may combine in three ways for three different geometries of face mills: negative radial and axial, positive radial and axial, and negative radial, positive axial. Face mills may be coarse pitch, fine pitch, or extra fine pitch, depending on the number of inserts relative to the tool's diameter. The coarser the pitch, the larger the gullet size. Milling inserts with a large